Hey everyone, welcome back. We've talked about using impulse and momentum theory to answer questions about inelastic collisions. Let's take that theory and let's apply it to this problem. We have a person, this person is playing tennis or racquetball. They have a ball that they're hitting and this ball is getting launched at a wall. The information that we have, we know the initial position, so where the ball is when it leaves the racket, and we know its initial speed. And also we're going to say that we know some coefficient of restitution for the interaction between the ball and the wall. What we want is we want the location of the second bounce point. And then we also want the velocity going into the second bounce. Now when I say second bounce compared to first bounce, depending on how we launch this ball and what the dimensions are, right, how far this is away from the wall, it's possible there are some initial conditions where the ball just kind of drops, right? Let's assume that this ball is going to get hit fast enough and with appropriate initial velocities such that it strikes the wall. Now, when it hits the wall, it's going to bounce off of the wall and then it's going to come back. So let's say it comes off of the wall and then it drops and it hits the ground. So there was the first bounce point was the contact with the wall. It's going to come off of the wall, it's going to hit the ground, and then it's going to come back up. So what we would like to answer is we actually want to know where is this second bounce point. And we want to know how fast, let's say how fast is it going, coming out of the second bounce. So we want to know where this thing's going to hit and how fast it is coming back at the person. Okay, so what do we expect the solution to look like? What's our approach? Well, the ball is going to leave the racket, and we know that it's going to move and then it's going to hit the wall. So in between the racket and the wall, then there's a ballistic phase. So let's start with this ballistics. Okay, and we've analyzed ballistics before. We know what those equations are going to look like. After it impacts the wall, or when it impacts the wall, there's going to be an impact event. After the impact, something is going to change in its velocities. Again, inelastic collisions. So we need to, through this impact phase, we need to solve for effectively a new set of initial conditions for a second ballistic phase, because now it's off of the wall, it's a ballistic again, and then it's going to be dropping down to the ground. So we have another ballistic phase, and then there is a second impact. Okay, so we've got ballistic number one, impact number one, ballistic number two, impact number two. The equations for the two ballistic phases, these are going to be the same. So really we could just write one set of equations for these phases, and what changes are the initial conditions. Initial conditions for the first phase, well, it's at a certain height and it's going to have a certain velocity coming out of the racket. And then initial conditions for the second phase are its trajectory coming out of the first impact point. So we need to solve for that second set of initial conditions using this impact analysis. And then from that ballistic analysis, we're going to end up with the states going into the second impact event. Those are the initial conditions for this impact event, and then we solve for the conditions coming out. And if we wanted to continue, we could bounce, 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 and then we would just switch back and forth between ballistic phase and impact phase. Okay, so where do we need to start? Well, let's take care of these ballistic phases first. To resolve this ballistic phase, we need to do the kinematics, we need to do forces, and we need to do the equations of motion. So let's put an inertial point in. I'm defining point in underneath the racket, such that the x-coordinate of the initial condition is conveniently 0, and then there's going to be some vertical component in its initial height. And of course we know that we need some inertial frame on this problem, so x in, y in, and let's treat body A like a particle so we don't have to put body frames on it. Now, we have done a ballistic problem before. We know what this is going to look like. We're going to have MA Q1 double dot in the X hat in and Q2 double dot in the Y hat in. This is going to equal minus MAG in the Y hat in. And just so we don't have to numerically integrate the equations, let's eliminate viscous air friction. Okay, so what's going to happen to these equations? We're going to do dot products and we're going to analytically integrate them. We will have Q1 double dot will equal 0. Therefore, Q1 dot will be Q1 dot initial, and that's going to be a constant value. So really what we're saying right now, Q1 is in the X direction, so if there is no viscous friction, whatever velocity it has, if we take this, this velocity VA and we break it into the X and Y components, whatever the velocity is in the X direction, in the absence of friction, that speed remains constant. We can numerically integrate this again. We'll get Q1 now, and I'll write it as a function of time. This is Q1 dot initial multiplied by time plus Q1 initial. Okay, and remember, we're saying that in this problem, these quantities are both known. So we're going to assume that both of these values are inputs. Next. If we solve for Q2 double dot, we take the equation of motion dotted in the Y hat in direction. Q2 double dot will be negative G, numerically integrate Q2 dot as a function of time, minus GT plus Q2 dot initial, and then Q2 as a function of time, negative 1/2 GT squared plus Q2 dot initial multiplied by time plus Q2 initial. And of course, if you're concerned about doing this, we have the video just on ballistics. Feel free to go back and check it out. All right, so we have these equations. How are we going to use these equations to solve these ballistic phases? Well, quick sketch of the problem. Remember, we've got a wall and we've got some space. Our object is starting at an initial condition like this. It is aligned with point in the X direction, and there is some vertical offset in the Y. What's going to happen? Again, we could pick initial conditions that are going to have all kinds of trajectories. We're going to assume that an initial condition is selected such that it strikes the wall. Now, the only part of this is just that it's going to hit the wall. I'm not saying it's going to hit the wall high. I'm not saying it's going to hit the wall low. Just that it is going to hit the wall. If it's going to hit the wall, and we can make that assumption, that means that ultimately the first thing we need to go looking for is time. So which of these equations can we use to find time? Well, what stops the trajectory? Does it hit the ground or does it hit the wall? In a very general case, we wouldn't know, right? If we were going to fully generalize this problem, we would need to figure out, does it hit the wall or does it hit the ground first? In which case, you would take these two equations, let's call them equation number 1 and equation number 2. We could use equations number 1 and 2. We could say, all right, take equation 1 and set the left side equal to some value, right? Let's call this X, let's just call this L1. So it's the length or the distance to the wall. You could take equation number 1 and you could put an L1 on the left side, and then you can solve for the amount of time. So this is how much time does it take for the ball to travel through the space and to hit the wall. Similarly, we could take these equations. We could take equation number 2, and we could say, all right, is it going to hit the ground? Well, take the left side, and if it's hitting the ground, that means the value of Q2 is 0. take this equation and set the left side equal to 0. We have initial conditions, and then you can solve this. It's going to be quadratic, so you have two solutions. One of them is probably going to be negative, and then you take the positive one, and that is the amount of time required for this ball to drop and strike the ground. Okay, so we have equation 1 and equation 2, and depending on the values and depending on the distance to the wall, we're going to get different values of time. So which time would we use? We would use the shorter time. Whichever of these two events happens first. Does it hit the wall first or does it hit the ground first? So in your code, you would have some kind of logic in there to check which of the times and then where is the bounce point. So what we're going to do for this problem is we're going to say that it's going to hit the wall, which means we are responsible then for putting in some kind of initial conditions that actually make this thing hit the wall. So that just means you have to confirm your math once you've gone back and you've assumed some values. So we're going to take equation number 1 and let's use number 1 to find T1. So T1 is it's the time when the ball comes into contact with the wall. From the theory video, we said that time 2 was maximum compression, so that's a very small instant later. And then we're going to, what we want to know is we want to know what are the states at time 3. Time 3 is after restitution when the ball is now coming off of the wall, when it's separated. So number 2, step 2 now, we're going to, let's say, use T1 to find Q1 dot and Q2 dot at time 1. So we have, if we know time 1, how long does it take for this ball to strike the wall? We can use it in equations, we'll call them 3 and 4. Use T1 to find set. So let's say using equation 3 and equation 4. Okay, so we know how much time. I have equations for the speeds. It turns out that equation 3 says the velocity in x is constant. That's fine. Equation 4 says the velocity in y is going to be modified by this. If we had viscous friction in the problem, then we would simply numerically integrate these equations and we would get the numerical speeds that way. So if we do that, if we find time and then we use time to find speeds, we could also, and we're going to need to, number 3, we also need to use T1 to find Q2. And that would be equation number 2. All right. So this is the process for the ballistic phase. You have your equations of motion. You figure out how much time it's going to take for your ball to hit the wall, and then if you have that time, you can use that time to find the new speeds because you have equations for them, and we can use it to find Q2 at time T1. What's the usefulness of this? Well, after this first ballistic phase, we're going to go into an impact phase. And what we need in the impact phase is we need the speeds coming in. So we'll have those. And then why do we need Q2 at time 1? Well, Q2 at time 1 is the height. So that would give us this location of that first impact point. The height, this is going to be Q2 at time number 1. Will be that height. And why do we need that? Well, there's a second ballistic phase after this first impact, and we need to know from what height it's starting. So this becomes the initial condition for the second ballistic phase. So let's say that you do all this. Okay, what are we going to do next? Well, this then is going to go into the first impact. So we're going to use this info in the first impact. We'll get to those in a bit. Let's talk about the process for the second ballistic phase. So second ballistic phase, ball is coming out. It's going to have some new impact point. And we want to know where that impact point is, and we need to know what are the speeds going into the impact. The equations are the same. We have the same kinematic equation. What changes are going to be the values of things like Q1 dot, because first of all, Q1 dot is going to reverse direction, right? It was positive, and somewhere in the analysis it's going to need to go negative, so this value will change. The initial position of Q1 is going to change. It's not starting here anymore. Now it's starting at L1. And then the initial values for Q2 will change. We will be at a new height, right? And then the speed will actually remain unchanged. This, consider that, we'll see this in a bit, but the free body diagram on the ball has restitution and compression forces only in the x hat in direction. In an actual impact, yes, it would affect other things, but that analysis gets more complicated and you can go to graduate school and study it. So the setup then for the second ballistic phase, same questions. Here's our process. We need to find time, right? And it's not going to be T1 anymore. Now it's going to be some new window. So if the ball is leaving at T3 and we say it impacts at T4, then we need to know what is the window, right, between T3 and T4. So we're going to find a new time. We're going to use this time. Well, first of all, how do we find that time? Well, now we're saying that the ball's going to hit the ground. So we can use equation number 2 and say, all right, given an initial height and speed, and I know what gravity is, at what height are we interested in now? What's the value of Q2 when the ball has hit the ground? Well, it's 0. So you use this equation, you plug in a 0, and then you solve for time. So we have the time now. We can use the time in equations 3 and 4 to get the new speeds. And this time, the number 3 is going to change. And instead of finding Q2 at this new impact, now we'll be looking for the x coordinates. And that's simply equation number 1. So again, if what's the initial condition for the second ballistic phase? It's at the wall. So this would be L1, right? Whatever the value of L1 is. And then this Q1 dot we have solved for, this new speed, is the speed coming out of that first impact. Okay, so the process is effectively the same. All right, next, let's move on and let's talk about those impact phases. Let's start with the free body diagram. In this case, we have only body A. So here's body A. We know that there is gravity acting on this system, MAG. Now, when it's in contact with the wall, I can draw the wall if I want. There's going to be a compressive force between these. And similarly so this will be the compression phase, and similarly during restitution phase, we're going to have a restitution force acting on it as well. You don't have both of these at the same time, right? It's 2 distinct phases, but they act in the same direction. Now, side note, right, while we're working this problem, let's also just briefly talk about what happens if you're impacting angled surfaces. So in this case, we're looking at, in our example, we're doing a ball strikes a vertical wall and then strikes the ground. So conveniently, that's X hat in and Y hat in. If your object is striking a surface at another angle, there's a couple of ways you could do it. You could put a frame on this wall, and then you could define the motion of the ball in terms of that frame, or let's replace this with the force. So let's say FC. You would have, in your sum of forces equation, you would have something like minus FC, and let's call this the W frame, the wall frame. So XW. And then the compressive force in the XW direction will affect the velocity of the ball in the XW direction. So at maximum compression, for example, this ball will come to a stop in the XW direction. So it's not that this is impossible, you just end up with about twice as many equations, and you just have to pay very close attention to your frames. That's all you do here. All right, so in ours, we have these compression and restitution forces, and then we also have gravity. Do we need to be concerned with gravity? Well, in a real system, yes, of course. However, the impact window, right, the time of those impacts are very small. So if the impact only takes place for milliseconds, then gravity doesn't have a significant effect on the ball in that time period. Again, this analysis can become much more complicated, and you can absolutely include this in your impact analysis. For this class, right, let's ignore it, and let's just say that the contribution of it is very small, so we're not concerned with it. So what I'm going to do is I'm going to say sum of forces on A, and this is just for the impact phase. We're not concerned about gravity. We're going to have minus FC in the X in direction, so this would be compression. And then of course for restitution, we would have basically the same thing, minus FR in the X hat in. Okay, so what do we do with these? Well, remember that we took them and we put them into Newton's second law and then we integrated them. What we end up with is we'll say the integral from T1 to T2, this is minus FC X hat in, and this will be Ka at time 2 minus Ka at time 1. We'll get the specifics of what this is in just a moment. And then let's get the second equation for restitution. The integral of Fr, this is in the negative X hat in. This will be Ka at time 3 minus Ka at time 2. And then the bounds for this one are T2 to T3. All right, let's get these specifics for the linear momentum. So we know that linear momentum is mass times velocity, so this is ma multiplied by the velocity of the ball. Well, go back and look at how we define the ballistics problem in the other video, but VA is Q1 dot Xn plus Q2 dot Yn, right? So we're now just saying it's this definition at these two moments in time. So this is Q1 dot at time 2 minus Q1 dot at time 1, and those are in the Xn direction. And then we have the other two, Q2 dot time 2, Q2 dot time 1, and that's in the Y hat in. There we are. It's equal to that. And then the last one, right? This one's basically the same thing. We just replaced the T2s with let's see, yeah, T2 is going to become T3 and T1 is going to become T2. There we go. So MA Q1 dot T3 minus Q1 dot T2 Xn plus Q2 dot T3 Q2 dot T2 Yn. All right, so here's our two equations, our compression and our restitution equation. This is integral of FC negative X hat in. Oh, and I've been leaving off the DTs as well, and all this other syntax that goes with it. Okay, FR minus Xn dt T2 to T3. All right. So here's our equations. What are we going to do for this impact? How are we going to solve it? Well, what information do we have? We're going to have from the ballistics, we're going to say that Q1 dot At time 1, this is known. And it's also a constant because we didn't have any viscous friction in those in the model. Next, we had Q2 dot at time number 1. This was known. This is actually going to come from equation number 2. This was equation 4. There we go. So equation 4 was the equation for Q2 dot as a function of time. So you solve that one for that. Next, what else do we know? Well, we know that this force, the compressive force, is only acting in the x hat n. Restitution force only acting in the x hat n. So they're only going to affect the momentums in the x hat n direction. What does that mean for the y hat n direction? Well, if we took these equations and we did a dot product with them, with the y hat n direction, then that means the left-hand side is 0, and 0 is going to equal ma q2 dot time 2 minus ma q2 dot time 1, which means that q2 dot at time 2 equals q2 dot at time 1, and we could go ahead and do the same thing to the third equation, and we're going to get q2 dot at time 3 also. So we immediately see then that this compression and restitution force, they cause no change in the y hat n direction. So we could actually take these equations and we can do the other dot product. We can just dot product them with x hat n, and that immediately eliminates these y hat n terms. Okay, so let's take off those x hat n's. Keep these bound. All right, dt, dt. Okay, what do we need to do next? Well, we actually have information about what happens at time 2. Remember that time 2 is defined as maximum compression. Well, what is the velocity of the ball going to be when it's at maximum compression? That means it hits the wall and it comes to stop, and then it's going to start coming back out. So at time 2, these values are actually 0 at the maximum compression. Okay, that means we can simplify a little bit more. Equation number 1, I'm going to leave the left side as is, and this is going to equal ma q1 dot time number 1, and it is negative. The last equation, this is ma q1 dot at time 3. Next. We also have the definition of the coefficient of restitution available to us. We said that we're going to assume some value of it. We know that this is equal to the integral of fr divided by fc. Remember, this was Poisson's definition. I can then say that really this is E sub r multiplied by the integral of fc, and that is equal to the integral of fr. All right, I have integral of fc on top, I have integral of fr on bottom. If I replace, let's say I replace on bottom fr with fc, so let's replace the r with a c, and let's put negative er in front. Okay, what do we do next? Well, I actually have a definition for negative integral of fc. So I can take this equation and I can put it in right here, and what's going to happen is we can actually replace this, right, and it has the negative on it to begin with, so that makes that would make the left side positive, and we're replacing it with a negative term. So tell you what, I'm going to write it in blue, and I'm going to put it right in the middle. These two equations set equal to each other. So we're going to have minus MA Q1 dot at time number 1 multiplied by ER, and then this will equal MA Q1 dot at time 3. All right, and let's check our signs and everything. So let's say in this equation, in this first equation before we insert it down, I drop the negatives and I make both of these positive. So then I'm taking this positive value and I'm putting it into this equation, and it has a negative on the front. Okay, so that we end up with this. So what can we do next? Well, we've got MA on both sides, so I can just remove the MA. Those are going to cancel. And then I have the value of ER, and I have the value of Q1 dot. And then I solve, well, Q1 dot at time 1, and then I literally just multiply these together, and I get Q1 dot at time number 3. This new Q1 dot at time 3, this is the new initial condition for the next ballistic phase. Remember that the Q2 dot remained unchanged, but the value of Q1 dot now, you would update it with this one. Okay, what we can do next is let's go ahead and let's do the second impact, which we know is going to be very similar to this first analysis. So impact number 2, what's going to be different? Well, coefficient of restitution is the same, so we can leave that one on top. Let's do another round of free body diagrams. This time we have gravity, MAG, and now in the second impact, remember that we're saying the ball is coming off of the wall and now it's going to hit the ground. When it hits the ground, it's going to have compression and restitution, compressive and restitutive forces. So FC and FR now point up. So if we take this free body diagram and again, we make the assumption that gravity is not going to have much effect, and we build the compression and restitution equations, we'll have the integral of FC, and I'm just gonna write integral of FC y hat n. We know that there's bounds and there's the dt's on it. Take note that this time it's positive, not negative, because the compressive force is acting in a positive direction. All right, so MA, and we know that it's, what are our bounds now? We're gonna say that, let's see, we went T1, T2, T3, that was the first impact, so the next impact is gonna be T4, T5, and T6. So we need this first period, then we'll write the bounds for this one just to have it down there. This is going to be T4 to T5, and then T5 is the new max compression. So Q1 dot T5 minus Q1 dot T4, and that is XN, plus Q2 dot T5 minus Q2 dot T4, and that is YN. Okay. Before we write the equation for restitution, similar process this time. The force now acts only in the y head in direction, so the velocities in the x direction are going to remain unchanged. That means we can do a dot product on this, and we can drop all of these terms in the y hat in direction. So what I'm going to do is just take this, turn these ones into twos. Q2, all right. And we can drop the y hat in from the left. So feel free to go through and do the full expansion for the restitution phase. You're going to get this. FR will equal MA Q2 dot T6 minus Q2 dot at T5. All right, What else do we know? What about maximum compression for this problem? Well, at maximum compression, your ball has hit the ground and it has come to a stop. So Q2 dot, right, in the y-heading direction at maximum compression is going to again be 0. So this quantity is equal to 0 and this quantity is 0. And we have MA Q2 dot at time number 4. And we have MA Q2 dot at time 6. Okay, so you take these two equations, you use the definition of the coefficient of restitution, and now we can relate the incoming and outgoing quantities. We're going to get an equation very similar to what we saw last time. Minus MA Q2 dot at time 4 will equal MA Q2 dot at time 6. And of course we can drop the, I left off the coefficient, right? So drop the MAs and this is minus ER. There we go, left off the coefficient. Now, one comment about this E sub R. This could be a different E sub R than the first bounce, depending on material properties and speed. If it were, for example, a tennis ball is a compressive body. The rate of compression is going to change its internal damping. So you could have certain energy loss at high speed. You could have different energy loss at low speed, or depending on the geometry of the ball, right? If it hits on a certain side, if it hits on a different side, etc. So these values can change. Okay, so given all of this, we have all of these analytical equations. What's next? Well, all that's left now is we just assume some values, and then we take those values and we put them into the equations, and we see what we get. So I have some values that I assumed, and I put them into MATLAB. Let me erase this, and I'll list out the values, and I'll tell you what results I got. I've assumed certain values. I wrote a MATLAB script that solved the equations, all the same ones we went through before. Let me put these constants on here. So L1, I said L1 was 10, and remember L1 is the distance to the wall. I gave the coefficient of restitution as 0.7, and I used the same coefficient for both impacts. The initial conditions, so Q1 at time 0 is 0. Here's where I put point in, so it's aligned with there. And Q2 at time 0 was 1. So maybe a meter off the ground when you're hitting this ball. And then the initial speeds coming out, so this is VA at time 0. That's Q1 dot at time 0. I gave as 25. So 25 meters per second is about 60 miles an hour. Q2 dot at time 0 was 3. So that means when the ball came out, it's just slightly above a horizontal shot. So that's going to give us, a nice arc into the wall. All right, so using these, what do we find? Well, we find our trajectory to the wall, and we find the first impact point. The information about that, time 1 was 0.4, and I found this height to be 1.42. Again, that's the value of Q2, right? It's the value of Q2 at time number 1. I got, and then the velocities going into the impact. So the velocity in the x direction going into the impact is constant because again we took out friction, and then the vertical velocity going into the impact. So let's say Q2 dot at time number 1. This is negative 924. Okay, so that's the velocity in the Q2 direction going into the impact. So a more accurate way to draw it would actually be a trajectory like this, where it hits a peak and then it starts coming back down, because the velocity, as we calculate, the velocity in the y direction is negative, so the ball's actually hit the top of its arc and it's coming back down just a bit. All right. Next, so we performed this impact analysis. What's going to change? Well, the vertical velocity is going to remain unchanged, and then the x velocity is what is going to change. So in this first impact analysis, we're going to solve for Q1 dot at time number 3. Time 3 is just as the ball is separating, so it goes into the impact at 25. It is leaving the impact at negative 17.5 in the x direction. Okay, we have these. We put these back into those same ballistic equations and we solve for time. We find that the ball is going to come back. It's going to strike the ground. So I have this in 2 ways. The time window for this second trajectory, we could write it as T4 minus T3. If T4 is the actual time where this thing hits, and we're interested in the window, then we want T4 minus T3. That time window is 0.451. So the actual value of T4 then is 0.851, right? Take so that's actually the value of T1, but again, we're using impulses and we're saying that the window between T1 and T3 is very small. So so we get this. What we need to go into this second impact? Well, we already have the velocity in the x direction. It was negative 17.5, and without friction, it remains constant in this bounce, so we don't have to recalculate that. We do need to know the velocity going in, so we need Q2 dot at time 4. And again, you can use those ballistic equations. If you know the time, you put it into the ballistic equation, you get the speed, and the speed going into the impact is negative 5.35. We perform the impact analysis and we find the speed coming out of the impact. This is now Q2. Q2 dot at time 6. So the Q2 dot at time 6, this came out to be 3.75. And then we also want to know where this second impact is. Well, the y component is clearly 0 because it's on the ground. So we want this distance, and let's call that distance L2. How do we find L2? Well, we have the time and we have equations for the ballistics in the x direction. So L2, you put it into your equations. L2 comes out to be 2.1. 2.1. So the ball leaves the racket, it travels through an arc, it reaches some maximum, it comes down just a bit. This 1.4, there we go. So it's that height, so it hits a little bit higher on the wall. It comes off the wall at a reduced speed. It strikes the ground about 2 meters, or whatever units, right? We say meters, about 2 meters in front of the player. And we have solved for the speeds coming out, and the speeds coming out are going to be negative 17.5 in the x direction and then 3.75 in the y, so it's going to come out and it's going to be headed back at the player so he can hit it again and return the serve. All right, so this is how you do these impact analyses problems. You have ballistic phases, you have impact phases, and the states from the ballistic phase become the inputs to the impact, and the outputs of the impact become the input to the next ballistic phase. And this only really gets more complicated. One, if you're doing objects striking, angled surfaces, you just have to do dot products and be mindful of the fact that the compressive force brings the body to a halt in that direction. And of course, if you want to do it with three-dimensional bodies that have orientations, there is some very impressive research out there talking about how you can actually simulate bodies with orientation and spin and all kinds of stuff having impacts. Okay, so that's it for this video. You should be able to solve that last homework problem on homework 10 using this. So best of luck, everyone, and I will see you later.